We now continue our discussion of conformational analysis by considering the molecule butane, which is going to be, as we're going to see, a little more complicated than ethane is. Okay, so here's a picture of butane. Okay, butane has 4 carbons, a CH3, carbon 1, CH2, CH2, and another CH3 on carbon 4. Okay, so we can also draw a Newman projection for butane, and what's going to be most useful is looking down the C2-C3 bond. So I'll take my model and turn it around towards you. So you can see on the front carbon from your perspective, there's a CH3 going up, 2 hydrogens going down, 1 to the left and 1 to the right. And on the back carbon, there's a CH3 going down, 2 hydrogens going up, 1 to the left and 1 to the right. Okay, so how is butane going to be different from ethane? Well, butane can also rotate about the C2-C3 bond, and we can make an energy diagram for that rotation, just like we made the energy diagram for ethane. Okay, so I'm going to start with 0 degrees being the conformation with a CH3 pointing up on the front carbon and a CH3 pointing down on the back carbon. If we rotate by 60 degrees, so this is a staggered conformation, if we rotate 60 degrees, we get to an eclipsed conformation. If we rotate 60 more degrees, we get to another staggered conformation. But unlike the case of ethane, in this case, the 120 degree conformation is not the same as the 0 degree conformation. In the 0 degree conformation, the 2 CH3s are as far apart from each other as possible. In the 120 degree conformation, it's still a staggered conformation, but the CH3s are somehow a little closer to each other, and we're going to have to take that into account. Rotate another 60 degrees, and we're at an eclipse conformation, but in this case, not only do we have the hydrogens eclipsing each other, but we also have these methyl groups eclipsing each other, and we're going to have to take that into account also. Okay, 240 degrees gives us another staggered conformation that looks like the mirror image of the 120 degree conformation. 300 degrees gives us another eclipsed conformation that's the mirror image of the 60 degree conformation. And finally, 360 degrees takes us right back where we started from. Okay, so we fundamentally have 2 different kinds of staggered conformations and 2 different kinds of eclipsed conformations. And so that we're all on the same page, I'd like to introduce some terminology that we use for each of these conformations. The 0 degree conformation with the 2 methyl groups as far away from each other as possible, we call the anti-conformation. That's a conformation, that's a term that everybody is going to use, and it's simply the staggered conformation with them as far away from each other as possible. The other staggered conformation, the one at 120 degrees, is called the Gauche conformation. Okay? Gauche is a French word. It translates literally as left, but people who have studied French may also realize that gauche also translates more figuratively as being wrong. And relative to the anti-conformation, the Gauche conformation is kind of the wrong conformation because these methyl groups are closer to each other. In the Newman projections that you see on the energy diagram, those methyl groups occupy adjacent positions in a Gauche conformation. As you can see from the diagram, the Gauche conformation is higher in energy than the anti-conformation by about 4 kilojoules per mole. That is not as much higher in energy as an eclipsed conformation is relative to a staggered conformation, but the Gauche is still a little bit higher in energy than the anti is. So I also have terms that I use to differentiate the two eclipsed conformations. These are not terms that you'll find in a textbook, but they're terms that I like to use just to differentiate them. And that is the case of what I'm going to call partial eclipsed versus total eclipsed. Now, even though I like to use these terms, I'm going to admit that they're somewhat of a misnomer, because in both of these conformations, the bonds are completely eclipsed, whether it's that conformation or this conformation. But I call the highest energy conformation, the 180-degree conformation, total eclipsed, because not only are the bonds eclipsing each other, but the methyl groups are eclipsing each other also. And in the partially eclipsed conformation, the bonds are eclipsing each other, but the methyl groups are not eclipsing each other. So, as you could probably imagine, the totally eclipsed conformation, where these methyl groups are really close to each other, is going to be higher in energy than the partially eclipsed conformations, where the methyl groups are, for all intents and purposes, out of each other's way. Okay, so this brings in another term called steric crowding. That is another energetic destabilization due to atoms being close enough to each other that they can bump into each other. Okay, so the Gauche conformation, which is staggered, and the total eclipse conformation, those two conformations suffer from steric crowding, and the value of the steric crowding is about 3 to 4 kilojoules per mole. So as you can see, the Gauche is higher than the anti by about 4 kilojoules per mole, and the totally eclipsed is higher than the partially eclipsed by about 3 kilojoules per mole. So in summary, there are 4 different energies. Anti is the lowest energy, total eclipse is the highest energy, and then you have the partial eclipse conformation, and you have the Gauche conformation. Both of the eclipsed conformations are higher in energy than both of the staggered conformations. That destabilization due to torsional strain, at least in butane, is greater than the destabilization due to steric crowding. If you really get molecules that are really, really large and steric crowding becomes more severe, it could have a greater energetic destabilization. But for butane, torsional strain is the bigger energy.